Dave again, here with another question from your Hayes and Harris Math SL textbook. This is Chapter 3H.2, Question 3. In this question, we're looking at exponential decay equations. We have the weight in grams of a radioactive substance remaining after t years, given by this function here. So that's the weight, and that's the number of years that we're going to wait for the weight to change. We want to find the initial weight. So for part A, we're going to find the weight when no time has elapsed, when t is 0. So that's going to be 1,000 times 2 to the power of negative 0.03 times t, except t is 0. So that's times 0. 0 times 0.03 is 0, and 2 to the power of 0 is 1. So the initial weight is 1,000 grams. Part B says find the weight after 10, 100, and 1,000 years. So we're going to let t be equal to 10. That gives us 1,000 times 2 to the power of negative 0.03 times 10. We're going to have to turn to the calculator to solve that. So jumping into the calculator, we have our equation. 1,000 times 2 to the power of negative, wrong negative sign, sorry. That's the subtraction sign, that's an operator, that means do an operation. This is the negative sign, that's the one that I want. Negative 0.03 times 10. Alright, we get 812 grams. We're going to let For part 2, we're going to let t be equal to 100. That gives us 1,000 times 2 to the negative 0.03 times 100. And I'll turn to the calculator again, but I already have the equation typed in, so I'm just going to scroll up, press enter, and change 10 to 100. 125 grams left. Part 3, just going to let t be equal to 1,000. So I have 1,000 grams times 2 to the power of negative 0.03 times 1,000 years. And once again, I'll type it into the calculator, but I'll do it by scrolling up, press enter, change 100 to 1,000. Yikes, that's almost 0. That is 9.3 times 10 to the negative 7. 9.3 times 10 to the negative 7. That's just the calculator's way of expressing scientific notation. This capital E right here. That's 9.3 times 10 to the power of negative 7, or something very small, 0.0000093 grams. So pretty much nothing left. Part C says graph the weight using the information in A and B only. So don't use the calculator to graph it, just sketch it. Time's not going to be negative, the weight's not going to be negative, so I only need quadrant 1. This is going to be the weight, this is going to be time. Time's going to go all the way out to 1,000 years. So there's 500. 1, 2, 3, 4, 5. So there's 100 years. And there's 10 years somewhere in there, something really tiny. We need to go all the way up to 1,000 grams. So there's 1,000 grams. 50 grams, 500 grams, 100, 200, 300, 400, 500 grams. So what do we know? We know initially there was 1,000 grams. After 10 years, there's 812 grams. So it goes all the way down to 812. I'm going to need some dashes in here. 1, 2, 3, 4, 5. So 812 is going to be right about there. So that's the coordinate x, comma, y. After 100 years, there's 125 grams. So out here at 100, we're down to 125 grams. And all the way here at 1,000 grams, 1,000 years, we're at 9.3, something ridiculously small, basically 0. 9.3 times 10 to the negative 7 grams. All right, so what does this curve look like? Well, it's an exponential decay, that's for sure, but it's pretty steep. I don't know if I can draw it very well. Oops. Something like that. So the amount of radioactive substance drops off pretty quickly. After 100 years, we have just over 10% remaining. 12.25% if you like.